I said already, my name's AJ. Um, so a little bit about me. I graduated in 2021, and I got an ATAR of 99.15. Right now I'm studying this thing called Bachelor of Philosophy at the Australian National Uni. But it's even though it says philosophy, it's all like sort of bio and like chem stuff. But yeah, I think my email's on this slide. So aj@tutesmart.com. So if you've got any questions, it doesn't have to be about Spesh. It can be about anything. Just feel free to shoot me an email, and I'll probably get back to you over the weekend. Um, so yeah, I love getting questions. It's kind of fun, something to do, and just like answer them. I've already talked about answering questions via Slido, and asking questions via Slido. Um, but yeah, definitely do. Feel free to email me at any time throughout the year, like even tonight. Um, so yeah, don't feel shy about that. Alrighty. So a little bit about Aitono's lectures. Um, so I think they started like 2010-ish. And it's just primarily it's been a lot of free resources for high school students just to even out that playing field. One of them is obviously this lecture that you guys are in. I think other things that they also have are, the online forum that which it started out as initially, study notes, newsletters. We have the ATAR calculator, which I thought was pretty cool. If you guys are doing a uni extension subject, I think the ATAR notes one is the only one that might include the uni extension increment. So that's pretty cool. And we have, some like online videos that will like specifically target like a few topics. So yeah, check that out. And it will probably be helpful. Um, on top of that, we also have TuteSmart, which is like our tutoring, like one-on-one and group class tutoring thing. So I do methods. I take the methods 3 and 4 group classes, and I also do special one-on-one and methods one-on-one, chem, and all that stuff. But more on that later. We also have study guides, and Ed Unlimited is basically all of our study guides and NEEP and a bunch of other practice exams and by different companies, all just thrown into one place on like an online library. So yeah, pretty cool. Okay, so Spesh, let's see what you guys have said about it. How do I? Is it this one? Show polls. Okay, so I guess the biggest word here is challenging. Someone chucked up sadistic, um, complex, exciting, hard work, and fun, amongst others. Like proofs, hard, unique, it's a headache. Um, you know what? I like agree with all of this to some extent. Spesh unfortunately can be pretty sadistic at times. Especially I don't know about the 2022 exams. I didn't look into it too much, but in 2021, I think we had a really really low average for our 3 4 exams. It was something insane, like getting like a 60% on exam 2 could get you an A plus. Um, so it was a bit crazy in my ear. I think they made it very physics based. But I don't think you guys will have that issue, just mainly because they've removed a lot of the kinetic stuff. Um, but yeah, who knows what the exam is going to look like this year? Probably could be more sadistic. But one thing about Spatch is that it is really, really rewarding. Because, if you put in the work and like, get through those challenges, at the end of that, you have like a crap load of scaling waiting for you at the end of the day. So, yeah. Also, the content itself is like pretty interesting, I think. I'm gonna stop this poll. Thanks for, throwing answers in here. Um, okay. Again, feel free to ask questions on this. I'm not sure if this is just being slow. Because I remember seeing a couple questions before, and they're just not here. But that maybe it'll appear later. All right. So with Spesh, at least in the previous years, exams have been really, really repetitive. So if you guys go back and look at exams from like 2010 up to like 2021, just having a glance, you'll see that they're really, really predictable. They're all sort of like, that same sort of like same order. Question one is always going to be like a rational functions graphing question, and so on. Like things like that. It's really repetitive. So with enough practice and enough practice exams, it's a really predictable subject. And the reason it's like that is because examiners know it's a difficult subject. Like content wise, it's really hard. So I guess they didn't want to make the exam itself like really, really hard, right? Otherwise, special would be even more hard. Um, I think I was talking about this in the methods 3 and 4 lectures as well. Um, what they do in methods is they know that the content is relatively easy, so then they make the exam super challenging. It's the opposite thing with special. I definitely think it's worth that extra effort compared to other subjects, just because of that insane scaling. It can pretty much carry your ATAR, I think. It did for me, anyways. Um, and yeah, don't be too intimidated by spec, because high school has always been a lot about the amount of effort you can put in. Or it's nothing to do with how like innately intelligent you are or anything. Um, I remember in year seven, I failed both my maths exams, and that theme sort of continued until like year 10. Like in year 8, both my mid semester maths exam and my end of year maths exam, I got 45%. So I would definitely wouldn't consider myself like cracked or anything at maths. It's just like a lot of effort. Um, but yeah, I think it's probably one of the best VCE subjects. I think the only subject I enjoyed more than spec is physics. But yeah. Alrighty. So today's plan, I thought we'd cover, two sort of like old topics that are going to stick in the study design this year, and probably the two sort of most assessed and two biggest sort of topics, apart from calculus. So we've got vectors and complex numbers. So we'll have a 15-minute break in between, hopefully. I haven't managed to have a full 15-minute break just because of time constraints. And obviously, I'll be taking questions through Slido. And so there are also a couple practice questions scattered throughout. So definitely have a go at them. And yeah, I think I might move this a little bit back just so I can get my hands in because I am gesturing. I just realized it doesn't come up on the camera. So yeah, all right, well, let's get going. Okay. Um, Hopefully you guys have come across vectors. I think my teacher briefly covered it in year 11. It might be on the study design. Um, I'm pretty sure it is. So hopefully you guys have come across it before, and this really is just a bit of a recap. Um, and another thing to keep in mind is Special 3-4 is going to extend a lot on concepts you've already learnt in Special 1-2. And this doesn't apply to all concepts though. It's just really vectors, complex numbers, and a bit of calculus. But there is a crap load of new things that are going to be introduced as well. So keep that in mind. I think the question I saw earlier was like, how do we revise for spec given that there's going to be, so much new things that are going to be thrown at us? I think the best two things to revise now are vectors, complex numbers, basic graphing, um, trying to get really really good at graphing. So what my teacher was telling us was the more lazy you are in maths, the better you are. Just because like if you're too lazy to draw out a graph, you'll get pretty good at visualizing graphs in your head. So do things like that. Get really good at like doing simple things like visualizing graphs in your head, getting quick at solving equations in your head. But always keep in mind that solving equations in your head just to like speed run things is not the best way to approach questions. It's just a good double checking measure. Anyways, so yeah, revise things like vectors, calculus, and complex numbers. And if you do that, I think you're pretty well set to start year 12. You'll definitely be doing better than a lot of other people. So yeah, all right. So um, before we begin, there are three sort of main things when answering any question in generally any subject or any STEM subject, I think. I know it says maths here. I think we can sort of extrapolate this because I did use all of this for basically all my subjects. So what you want to do when you see a question, read it blank the first time. Just skim through it, have a read, and then read it again. And now when you read it again, underline, highlight, draw the scenario out, and then do the question. Then read the question again just to double check your answer. and then check through your working out. Make sure every step is very clear, and pretend like you're the examiner, right? Pretend like you're marking your own exam. Be harsh on yourself, and try, like, yeah, I guess, like, be harsh on yourself, be fair with yourself, and try put yourself into that examiner's mindset, just so you can sort of like really assess if your working out is clear enough to get you full marks. Um, this drawing bit applies a lot to vectors. Other things it can apply to is like optimization, minimization problems when it comes to calculus problems, in methods and things. Um, you can also, generally, any question that's a worded scenario, it's always a good idea to draw things out. But for vectors in particular, just so you know, it's using funky arrows, weird letters, weird signs, weird squiggly lines. It's always a good idea to, convert everything from weird letters and numbers and gibberish into like actual visualizable graphs. So yeah. Um, all right. A couple notation things with vectors. You need to write the arrow on top, or you can do like the tilde underneath. So we'll try get an example. So you can either do these arrows on top, or another thing you can do, maybe it's on this. You can bold them. I mean, like on your exam, sometimes they'll come up as bold, um, but you always can't. It's not really possible always to do a bold. Alternatively, what you can do is, let's say you don't have the arrow. What you can do is do this thing called a tilde or like a squiggly line at the bottom. If you look underneath your escape key on your computer, it's probably there. I just can't draw that well with the mouse pad. So yeah. So either arrow on top or a tilde on the bottom underneath your letter. Um, it's kind of unfortunate, but that they can mark you down if you don't do this. Just because then it's not even a vector at that point, it's just a letter. I'll just scroll back to this. Another thing to note, if you guys do physics, so this might be a bit of an advantage, vectors are going to tell you directions, right? Vectors are directions and magnitude, where magnitudes are just going to be size. So magnitudes are just going to be the length and the size of that vector, where the vector component is really what's telling you the direction. But yeah, hopefully that makes sense. Okay, so like I just said, vectors are going to be arrows that show both magnitude and direction. So, for example, we've got moving 200 meters east or 50 meters up, meters per second up, and, this is going to tell us displacement initially here, and this here is velocity. So, definitely, a bit of an advantage if you've done physics before. Other examples are like, going 60 kilometers north in a car. That's a vector because you're telling, the magnitude, which is 60 kilometers an hour, and you're also giving a direction, which is north. But if I was to just give magnitude, that would be something like just going 60 kilometers in a car, and that's our speed. Whereas velocity is going to be 60 kilometers an hour. Alrighty. With our magnitude, it's always represented by the length of the arrow. So you can see that this arrow here, just by looking at it, we can see that its magnitude is greater than this arrow here or this arrow here. It's probably greater than that one. I just can't. Oh, yeah, I'd say it's greater than this one here. So this one has the largest magnitude. And the direction is always going to be from the head to the tail, right? So this one is going this way. So we're pointing in the arrow, the direction of the arrow. Oh, wait, sorry, tail to head, not head to tail. So that's our tail and that's our head. So we should always be pointing this way. This one here is going to be pointing that way. So another thing is that scalars are going to be magnitude only. So vectors, again, more physics terminology. Scalars are things like speed, distance, probably things like, or mind blank. I'm sure you guys can come up with a lot more examples than me. Time is always going to be magnitude, right? You can't really give a direction to time. I mean, I guess you can go, yeah, no, you can't really give a direction to time, I guess. So time would also be a scalar. So when we just, consider the length of this arrow, we're talking about scalars. When we're considering both the length and the direction, we're talking about vectors. So hopefully that makes sense. Oh, also, this one here, maybe some of you guys remember, but vectors are generally the change between 2 points, right? So we're going from, that's why this vector here and this one here are probably going to be equivalent. They're going to be parallel at the very least, because they're going from the same point, or they're covering the same change, right? They're covering the same, like, this is point A, this is point B, this is point O, and this is point C. The change from O to C is going to be the same as A to B. And we'll go into that more later, I guess. Okay, I'm just going to quickly get rid of that, all this drawing stuff. Alrighty. So vectors, we generally write them out like so. So we have what the vector is equal to, plus its I component, its j component, and its k component. You can also represent them as like column matrices, or the bold letter like we've talked about. And whenever it starts and ends at a certain point, we can have those point in capitals and then do an arrow above them. So in this example here, it's like starting at A, ends at B. We can do A to B. That's how I think about it. Like the tail of the arrow is at A and the head of the arrow is at B, so it's going from A to B. Another thing it's probably talked about in the next slide. Yeah, it's going to talk about direction components and unit vectors. So, okay, maybe not unit vectors yet. So I, j, and k are all unit vectors. If we draw them out in columns, so if you guys don't remember, a unit vector is going to be is a vector of length 1, with magnitude 1. So I is just 1 in the x component and 0 everywhere else. J is going to be 0, 1, and then 0. And like so on for K. Can't be bothered drawing it out, sorry. But yeah, it's going to be 0, 0, 1. That's all. And so the things that are being multiplied here are going to be scalars. They're just scalar numbers. So, they're just simple numbers like 5, 6, 7, 8, 9, 10. And the reason that they're there is they're changing the length of these unit vectors to make our overall vector. If that makes sense. I'm just going to switch back to the laser pointer here. So yeah, I, j, and k are direction components. I tells us things in the x-axis, j tells us things in the y-axis, and k tells us things in the z-axis. So I've already sort of talked about that here. Oh, I wrote an x. Should have been an I. This I should not be confused with the complex number I as well. Hence why there's, the arrows on top. I'm just going to switch back to laser pointer. All right. So position vectors are a special type of vector. They start with their tail on the origin and their head somewhere else. So the origin is always going to be represented as O, usually. So if I create some vector from O and I go to P, this is going to be the position vector, OP. Vectors can go anywhere as long as they have the same magnitude and direction. So I might have a vector like this. Technically, it's equal to OP. It's just showing a change in a different position. It might have the same components, but like different subtractions. It'll probably make a bit more sense when we go into that in more detail, and we actually start doing a couple calculations. But yeah, try think of vectors as like changing things, or things that show change in position or change in something. Easiest way to think about it is showing change in position on a three-dimensional area. All right. Just whenever we're doing the vector addition, just make sure we connect head to tail, and same concept with subtraction. So let's say also this is the tilde as I was talking about. It's just drawn out a little bit better here. All right. So let's say we have two vectors, A and vector B, and we want to add them together. The addition is going to be this line that goes from the tail of A to the head of B. You can see we've shifted across, right? This B has gone from here to here. But what you'll notice, or well, what should be true in this case, is that the length and the direction of B has not changed. So it's the same vector, regardless of if it's here or if it's there, it's the same vector. Okay, so now we start at the tail of the first vector and we follow it to the head of the next vector, and then we draw this line that connects them. And this is our new vector. And that's its direction that it's going to be facing. And we write it out as A plus B. Again, direction, magnitude, same, means it's the same vector. With subtraction, it's the same concept, but what we're going to do here is we're going to reverse that negative vector. Maybe you guys remember this, but let's talk about doing, let's say, same thing again. Actually, I'm not going to draw that out because it's sort of already drawn in. So let's say we're considering the same two vectors, A and B, but in this time we want to do A minus B. What's nifty is that we can switch this to A plus, in brackets, minus B. All right, so what does a minus mean in terms of vectors? If I was to multiply, a full vector by negatives, what would that happen to its direction? All right, so let's try figure that out. Let's say I get R, my vector R, and I put a negative in front of every single thing here. Would you guys have a thought about what that would, what's going to happen here if I multiply a vector by -1? You know what? I'll create a poll as well. So one of those free word polls as well. I'm going to create one. Create new poll, word cloud. What happens when I apply a vector by -1? All right. I'll let you guys have a quick go at answering this, and then we'll dive into the answer. Nice. So basically everyone got it. Good stuff. I'm probably going to stop the poll now. But yeah, thanks to everyone who answered. And if you do say reverse the direction, you're correct. Multiplying it by -1 reverses the opposite direction. Probably can't answer on this, but have a think as to why. Maybe someone can write up a quick justification and send it on this. But why does multiplying a vector by -1 cause a reverse in direction? I'll let you guys have a think about that. But while you're having a think about that, I'll sort of talk about it as well. All right, so let's say I have some vector. Okay, let's ignore this part of the graph. Let's say I have some vector going from, it's going to change the color. Let's say it's going from A to B. So we'll say this is A, and we'll say this is B. Let's say my vector is, I don't know, make it pretty simplistic. So X and Y only. I don't really want to get the K involved now, just because it's annoying for drawing it out in visualization. I'll also have to show you guys a neat trick later on. It's more physicsy, but it is a neat trick nonetheless. Okay, so we have a vector going from A to B. But what happens when, what would negative A to B look like, right? And, if we're struggling to visualize what that would look like, even though we sort of already know the answer from that poll, it's going to be just flipped. So it's like this. Um, okay. But what happens to every single component in it? Well, so we'll have the component x, xi. I'm not going to bother drawing in the arrows or the tildes just for time. Also, I'm lazy. But yeah, please draw them in when you guys do this. It's just annoying to draw things on the mouse pad. Okay, so we have xi, yj plus zk. But in this case, z is 0, so it doesn't really matter. That's going to not exist. So we've just got xi and yj. All right. Let's say this is not going to be x, just because this is not a unit vector. I could, or not a unit vector, a position vector. It might be easier if I do make it a position vector, but that's fine. And so this is going to be some number, you know. I'm going to call it, I don't know. I don't know. We'll call it theta. And the y coordinate is going to be something like, I don't know, something lame, c. Okay, so what x and y are, right, is the difference between the coordinates of a, so maybe, ax and ya, and we're subtracting that from the coordinates of bx or c and theta, right? So we'll say this one's like coordinates are xa and ya. So x, a, y, a. And so what we're going to do is we're going to find this x and this y. It's just the change in, that coordinate, right? So what this is going to be, we're going from a to b, right? So it's going to be xa minus theta. And well, actually, it's going to be theta minus xa, sorry. It's always final minus initial. And then this one here, this y here is going to be c minus ya, right? So write that out. So theta minus xa, and c minus ya. Okay, that's what happens when they're positive. But if I put a negative in front of them, I'm going to flip them around, right? So now this is going to become xa minus theta, and this is going to be ya minus c. So then, because we're going, since we're always following the rule of final minus initial, which is generally the rule for change, I'm just going to write change as delta, which is what it usually is in physics. So change is always final minus initial. And so now instead of, our final position being B, our final position is now going to be A when we multiply this by a negative. So we're just trucking a negative out the front here, which is why the direction switches. Sorry, I probably could have made that a little bit more concise. But yeah, that's another thing I sort of want you guys to take away from this. If you came to the methods lectures, you probably heard me say this a million times before. Maths, it's really important, apart from just grinding out questions, it's really important to ask ourselves why. Whenever someone tells us something, it's important to figure out why. And, it ultimately builds your understanding of the concept. I'm just going to quickly end this poll. But yeah, nice. Everyone got this right. I'm just going to end that one there. Alrighty, I'll talk about these questions in a squiz. Okay. I'll just check how long until the break. We have a decent amount of time till the break. But yeah, I'll make sure I answer all those questions during the break. Okay, so let's go back to subtraction. So I want to do tilde a plus minus, well, vector b, right? So all I have to do here is I'm just going the other way now. Same stuff, just the other way. So a tilde b. And that's going to be I'll probably shift it like this, right? So this is a Oh, actually, no. Another thing is that you need to sort of make sure that they're pointing in the same general direction. So that's why this would not work there. Um, oh, this is already pointing in the same direction. That's fine. Nice. It's going to be minus b. So I want to create the line from here. So that's the direction of the new vector. And all I do with the components is that I multiply the components of b by -1, and then I just sum them together. So like terms. So all the I components with the I components, you get j components with the j components, and the k components with the k components. It's just really that simple. Okay. Um, so how do we, given a vector, right? How do we figure out its magnitude or how long it is, right? If a vector is, xi, yj, zk, to figure out its length or its magnitude, all we have to do is square every single term in it. But why? Before I move on to parallel vectors, why is that true? Well, it's a pretty simple theorem, and you guys have definitely come across it before. I'm gonna start doing it. Oh my god! Wow. All right. No clue what happened though. My hand just like jittered. I'm gonna start with doing this in 2 dimensions, because once we start doing it in 3 dimensions, it gets a little bit more crazy. So we have x and we have y, right? If I make the vector OA, so OA, well, how would I go about finding the length? I'll give you guys a few seconds to think about that, and then I'll sort of spoil you. So, um, you know what? I'll let you guys. I'll make a poll for you guys to do. Create new poll. Word cloud. What theorem can I use to figure out magnitude? So my hint to you is that it's a theorem that you guys have come across in the past. Try look at this. It's 2 words. Try throw those on the L. Give you guys a couple seconds. Alrighty. Maybe a few seconds more. Okay, yeah, pretty sure. Everyone sort of has the same idea. It is Pythag. Um, alrighty. Okay, so simply all we do is get our x component, our y component, and we just want to find the magnitude, right? So we just square them, add them together, take the square root. Pretty straightforward. Another thing to note is that magnitude is always represented with these two like pipes. You guys have probably maybe come across it if you've done modulus functions. But yeah, it just indicates length, size, positivity, that stuff. All right. Let's talk about parallel vectors. So 2 vectors, if they're parallel, facing like the same direction, um, they can be, they're if they are parallel, or if they look parallel, generally they follow this mathematical property. So this is what we use, this mathematical equation here. That's what we use to, say that a vector is parallel. So sometimes they'll ask you, prove that these 2 vectors are parallel. And to do that, all you have to do is you need to show that there exists some k that is a scalar that fits that fits the bill. So, maybe you have 2 vectors, AB and AC, or OA, OC, and you need to show that they're parallel. All you really need to do is you need to factorize out one of them till it looks like K times OA, if that makes sense. Like, if we're trying to do something to OC to prove that's true, what we can do is we can sort of like factorize this K factor out, and then sort of manipulate our vectors around till it fits this. But yeah, so the reason that's true is because, two parallel vectors don't have to be of the same length or the same direction. So they can be like this, right? But if let's say, I multiplied this by some negative, some negative number, maybe like -10, what's going to happen to it is it's going to flip around and it's going to get stretched out, right? Likewise with this, if I multiply by -1/10, it's going to get flipped around and squished. So yeah, hopefully that makes sense. Alrighty. And then unit vectors. I talked a little bit about it when I was talking about the I, J, and K. Also, um, something to point out that these I, J, and Ks don't have any sign showing that they're a vector. They don't have the arrows, the J's. I mean, they don't have the arrows, the tildes, or they're not really in bold, right? They're not like a different color from the X, Y, and Z. So if I wrote that in an exam, I would be losing marks. But yeah, just thought I should point that out. Okay, so unit vectors, I was talking about them a bit before with the I, J's, and K's. They have a magnitude of 1, and they generally only specify direction. They're really like, you know, yeah, they're just like saying like north or east or south, or they're just pointing in a certain way. But their magnitude is always going to be 1. Um, one cool thing we can do is we can sort of like get any magnitude. So let's say, we know like the speed of a car, and we don't really know much except that the next car next to it is traveling north. What we can do is we can get the unit vector of this other car that's traveling in the same direction north, and multiply it by this magnitude that we have for this other car, and we'll get the vector for the car that the new car, if that makes sense. Sorry, that was very wishy-washy. But yeah, so it's pretty nifty. That's what its main use is, so translating directions across onto other things. So all we have to do to figure it out is we get our full vector, and then we divide it by its magnitude. The reason this works is basically what we're doing is we're getting this whole length of this vector, and then we're dividing by its own length, so that shifts down to 1. But it still has its vector component, right? But since it still has its vector component, it still shows us a direction. Alrighty, hopefully that makes sense. Okay, I'll give you guys a little bit of time to have a crack at this, and then we'll come back. I'll probably give you guys, um, I'll give you guys a minute or so on this one here, maybe a little bit longer, 2 minutes. Um, in this case, it's really important to draw your scenario out, just because I feel like visualizing, this and this is a little bit hard. So I'd put the points P, Q, and R just randomly using these relative position vectors. And then I'd put in point S, and then I'd try to figure it out from there. Okay, hopefully that was enough time to go through this. So I'll try to create a solution for it and walk you guys through. So we have three position vectors, P, Q, and R. One thing you'll notice is they're not in terms of A and B, um, or they're not in terms of I, J, and K. A and B are their own vectors. We don't know what they are. They're just the relative vectors that we're dealing with here. So we can't treat them the same as I, J, and K. That's an important consideration to make. Um, so 2a minus b doesn't necessarily mean, 2 away from 0 and 1 down from 0. It could really be anywhere on the plane. We don't really know what these vectors a and b are. All right, so let's try to draw this out. So I am going to pretend like they are I, J, and K vectors, though, just for the sake of answering this question. There are some circumstances where that matters, though, so keep that in mind. Okay, so we have the vector p. I'm just going to say that's 1, 2, minus 1. Yep. So that's p. Okay. And then we have vector 3a plus b. So that's probably going to be somewhere like here. So that's going to be q. And we have r. That's something like, so a and then 4b. So here. Okay, cool. And point S is on OP. So O is there. Such as that OS is parallel to OP. Okay, cool. So that makes sense. So it tells us, same direction. So OS is parallel to OP. Cool. And also that RS is equal to R, or is parallel to RQ. Okay, so part A wants us to express OS in terms of K, A, and B. Okay, well, I think this one's pretty straightforward. We just have to plug everything in to that parallel equation they gave us here, this relationship here. So OS is going to be equal to K times OP is 2a minus b, right? So 2a minus b. Cool, easy. That's probably 1 mark there. Okay. This is probably 2 marks as well, part B, and this is probably 1 mark. Now we want to find it in terms of A, B, and M. So I think step 1 is to figure out what R and Q is. Oh, it's also important to note that RS, this term here, is not going to be the same as OS. So we need to figure out a consistent way to go back from RS to OS. Okay, so first things first, let's try to figure out what RS would be equal to. I'm going to pull out a different color. So we have OS, OR. So OR actually, here's a neat trick with vectors. If we know that our final thing is going to be RS, the very first letter should be R. So we're going to go R, O, plus O, S. And when these middle terms are the same, they can sort of cancel out. And so what we're left with is R, S. So that's just a neat vector addition trick to know that you're going in the right direction. The middle terms need to be the same. If you're going in the right direction to add two things together properly, they're going those two middle terms are going to be the same. All right, so we have RS. That's what it's going to be. We can calculate RQ relatively easily as well. RQ is just going to be, again, RO and then OQ. So RO plus OQ. and that's going to give me RQ. Yep. Okay. And the last thing to do is to do RO. We can sort of do a bit of simultaneous equations here, because we know if I multiply this whole thing by m, these two are now equal, right? So equation 1 and equation 2 are now equal just by simultaneous equations. And so now I can do RO plus OS is equal to M RO plus OQ. Okay. Okay, and then from here we can solve. I'm a little bit lazy. I don't know if I want to keep writing all this out, but hopefully you guys get how we're going to go about this. Because we want to figure out OS, right? So one thing we can do is we can subtract RO to the other side. So we have OS is equal to, I'm just going to expand, put the M in both terms. So let's say we have MRO and MOQ, right? We'll have MRO minus RO, so that's going to be M minus 1 RO plus OQ M. Sorry, that's really messy. And then the last thing to do is to chuck in our vectors into here, and then expand and simplify. And that's all that's really left to do. One thing to mention is that RO is equal to negative OR. Hopefully that makes sense. Sorry I didn't go through and work it all out, but I just did everything in algebra and vector notation. Just because I can't, it's probably going to take me quite a while, and you guys will just be sitting here staring at the screen, probably really bored, as I randomly plug in numbers into here. Hopefully that made sense. If it didn't, feel free to throw a question up on Slido, or even after the lecture, feel free to email me about any of these. One thing I should remind you guys is that all of this is up online, like underneath the slide resource, and like the lecture is recorded and the slides are also underneath, like in a link though. All right, I'll give you guys a minute or so to have a go at this one here. So use your result from the previous one, and try work it out. Try use the fact that we sort of know what OS is in terms of both. Okay, let's have a go at this. Hopefully that was enough time for you guys to have a solid attempt. Maybe even get an answer. So what I'm going to do is I'm going to use the same result from here, and I'm going to sort of try figure it out from there. I guess I do have to work this out to get an answer. Um, so we'll see how that goes. Hopefully I don't make that many mistakes. All right. So the first thing I'm going to start with is I'm going to equate the result I got here and equate this result here. So I'm going to put them together. And then from there, I'm going to try work out what k and m are going to be. All right. So we'll have k 2a. Also, I'm not going to bother throwing in the tildes or the arrows again. I'm sorry. But please do this when you guys do your working out. Make sure you draw in those arrows. And then we'll have m minus 1 r naught ro plus m o q. Okay, so express OS. And so they want us to find k and m. Actually, there's just like that's probably not the way to go about it. Actually, just trying to think. Because I realized if we do this, we are not going to get to an end result that we want. Hmm. All right, so I've obviously made a mistake somewhere, or maybe I haven't. I'm just really brain dead. Find k and m. Okay, so generally when we have two variables, we need at least two equations. So this is probably going to be one of our equations. We just need to figure out what our other equation could be. So RS is probably something like that. RQ is also going to be. This diagram isn't the best, but they're about parallel, I guess. Feel free to throw suggestions in Slido. I'm clearly really like brain dead right now, so no clue what's going on here. Try to figure out without looking at those suggestions. Okay. OS. We'll look at Slido. All right. Hopefully you guys have thrown up some solutions here. Okay. Let's find K and M. Damn, I'm pretty sure I solved this question earlier. That is really a bummer. All right. So what I'm looking for here is that I need one more equation so that I can go about solving this. One more equation that is sort of like similar terms here. I mean, I guess I could try work out what OS is. That might be a way to go about it. Maybe the answer is a bit more obvious if I expand this. So we'll have a go at that. We'll actually try represent OS in terms of M. So here, I would get, so OS is going to be equal to, what is RO? So that's going to be negative AM minus 4MB plus OQ, which is 3MA plus MB minus RO is just going to be OR. So minus RO, which is plus A plus 4B. If I simplify that, I should get 2MA, 2M plus 1. Oh, yeah, no, I just realized. This is my bad. So I should get 2MA, 2M plus 1A. The reason I'm getting 2M plus 1 is what I'm doing is I'm collecting this term here and this term here, and then I'm adding the 1 from here. Sorry, I am skipping steps. Generally, this is really bad practice to skip steps. And this one here is going to be 4 minus 3M B. Okay, that's what OS is equal to. Yeah, the solution became pretty clear, I think, once I just drew everything out. So that's just probably really deserved of me being lazy. All right, so A plus 4 minus 3M B. Maybe you guys have come across this before, equating variables. So I have 2AK here minus BK. So one thing you can do is you can look at all the terms in front of A or related to A and all the terms related to B, and you can say they're the same, right? So for example, if I have 4x plus 1 is equal to AX plus C, we can sort of infer that, A is equal to 4 here and C is equal to 1. Right, so that's basically what I'm going to do with this, just considering the A's and the B's. So looking at all the terms in front of A, I could sort of guess that 2k is equal to 2m plus 1. So 2k equals 2m plus 1, and minus k is equal to 4 minus 3m. And then from here, I can sort of simplify and solve. So I'm going to resolve for k here. So k is going to be equal to 3m minus 4. And then I can substitute this equation back into our original equation. So then it's going to be 3m minus 4, all this times by 2 is equal to 2m plus 1. That's an m though. So this is going to be 6m minus 8 is equal to 2m plus 1. And if I simplify this, is going to be 6 minus 2, so that's 4m is equal to 9, and m is apparently equal to 9 over 4. I don't know if that's right. There's a chance it's not. It's actually a very high chance it's not. Because maybe I made a mistake with my algebraic manipulation here, because that was all pretty rushed. And then k apparently is 9 times 3, which is going to be like 20. Oh, mind blank again. So 9 times 2 is 18. What I'm going to do here, so generally whenever I have mind blanks like this, which happens a lot in exams, I split everything up into tiny bits. So I'll get 18 plus 9. Just to make sure I'm not making a simple mistake with this addition stuff here, I'm going to do plus 2 to this, so that's 20, 27. So apparently it's 27 over 4 plus, I'm going to convert this to, or minus, sorry, I'm going to convert that to 16, minus 16 over 4, which is probably 15 over 4. Alright, sorry about that. I have no clue what happened. I think I just blanked on all of this. So there is, hopefully this is correct. Maybe it looks sort of correct from memory, but there's a high chance it's wrong just because I rushed this step. So, so one thing you guys probably saw me do at the end was this one, which is a bit weird. And the only reason I did this is because like in high school, I used to make a lot of silly mistakes. If you've come to the other lectures that I've done, you've probably heard me say this so many times. Like silly mistakes were like the bane of my existence. And so, you know, it was simple things like doing 9 times 3 is like 24, right? Which is obviously not true, but yeah. And, you know, simple addition mistakes like this that could have happened here. I'm not sure. I'm not going to really go back and double check. But to prevent myself from making these mistakes, I do like really, really clear steps, which isn't shown here. But if I was doing this on pen and paper, I'd have one line per set of working out. I'd show like everything. I'd show, you know, instead of converting this to 16 over 4 straight away, I'd do 4 times 4 over 4. And then in the next step, I do 27 minus 16 over 4, and then maybe 27 minus 10, and then 27, you know, 17 minus 6. I realize that's wrong as well, now that I'm talking about it. Cool. But yeah, you can probably see how easily I make silly mistakes. And I feel like the easiest way to crack down on silly mistakes is just showing every single step. So what I should have done was 27 minus 10 minus 6. So that's going to be 17 minus 6, which is going to be 11. Yeah, that should have been blaringly obvious, but that's the thing with silly mistakes. They're not until you double check them. All right, hopefully that makes sense. I'm sorry for all of that there. I just made, yeah, too many silly mistakes. I think there was a question on how to avoid silly mistakes. This is one of those ways. Writing out every single step of working out, double checking yourself as you go through every single step. And one thing I like to do is like sort of talk to myself during my exam. Every time I do a step, I'd rerun that step in my head, just so I'm sort of like double checking everything as I'm going along. All right, so hopefully this question made sense. And yeah. Okay, so let's talk about multiplying vectors. Particularly, you know, the dot product. So maybe you guys have heard of the other way of multiplying vectors, which is the cross product. But you don't need to know that for VCE, just the dot product here. Okay, I'm just gonna pull out the laser now. All right, so dot product or scalar product. It's sort of like multiplying vectors together, but not really. So what we do here is we multiply the like terms when we do a dot product. So, you know, everything in front of I is multiplied with everything in front of I, and everything in front of J and K, you know, and so on. Okay, so here we're going to multiply the two A's, so we get A1, A2, and then we're going to multiply the two B's, so B1, B2, and then we're going to sum them together. Pretty straightforward, pretty cool stuff. But it's pretty important. So the full equation for the dot product, you guys might have seen this before, it's going to be cosine theta is equal to the dot product, so A dot B. And that is the angle between these two vectors, so that probably there is theta. So using that, we can try find the angle between two vectors. We can rearrange this. Also there's magnitudes out here. So magnitude of A, magnitude of B is out the front. Sorry, I almost forgot that. We can rearrange this in terms of cosine theta, and we'll get this. So pretty straightforward there as well. This is pretty important for proofs. Sometimes they'll ask, try show that vector A and B are perpendicular. Well, how do we do that? We need to use the dot product, and if you guys remember, cosine pi over 2, or cosine 90 degrees, which happens when we're perpendicular, is going to be equal to 0, right? So to show that two vectors are perpendicular, all we do is we show that their dot products are equal to 0. Okay. Hopefully that makes sense. Yeah, see, that's here as well. Whenever we do the dot product of the same thing, a dot a, what we end up getting is just the magnitude of a squared. The reason that makes sense is that we do, ai plus b and j. Let's say that this is a. If I take the dot product, what I'll get is a times a plus b times b, right? And that's simply a squared plus b squared. If we look at the magnitude of a, that's going to be a squared plus b squared and then the square root of that. And so then really this is the magnitude of a squared. All right, hopefully that makes sense though. All right, have a go at this. I'll give you guys a couple minutes, maybe a minute or two on this one. I've already sort of talked about it. Kind of spoiled the question, to be honest, but hopefully you guys can have a go at this still. Alrighty, hopefully that was enough time there. Let's sort of walk through it. Probably not going to spend too much time on it just because I've already talked about it earlier. So to show that A, and B are perpendicular, given that, so I'm just going to write, given that A is perpendicular to B, A dot B, or cosine theta, where theta obviously again is the angle between A and B. I would write that down, saying a statement that theta is the angle between A and B, is 0. A dot B is equal to the magnitude of A times the magnitude of B times cosine theta, and then as cosine theta is 0, A dot B is also 0. Obviously, when you write out a proof, you want it to be a lot more formal. So instead of just skipping this step here, I would say, given that cosine theta is 0, as theta is equal to pi over 2, A dot B is also equal to 0. So yeah, hopefully that makes sense. Have a go at this as well. Probably give you guys a couple minutes on that one. Okie dokie. Hopefully that was enough time to do this. All right, so whenever we want to find OM, um, so I assume this is um, AB. So we want to find first the midpoint. So I'm just going to draw out a scenario here. So this is here is A, and I assume B is probably like this. So we have the vector AB, and M is here. And what we want to find is this here. We want to find OM, right? So what we can do is we can find the position of AM, and then we can sort of backtrack. So first step is to find AB, right? Step 1, find AB. So AB is going to be equal to AO plus OB. And that is going to be the negative of this plus this. So that's going to be 2 minus 1. So that's just going to be I plus 1 minus 1, which is going to be 0. And minus 1 minus 1, which is going to be minus 2k. So AB is equal to I minus 2k. So then AM, so this implies AM, sorry, I'm going to stop that up. AM is going to be equal to half of that, so minus 2k over 2. And now from here, what we do is we find, we basically do the same thing here. We go AO and then OM, and then we rearrange. So to find OM, what we're going to do is we're going to do A, so we're going to do OA plus AM. And that should give us our answer there. So OA is going to be equal to, again, I plus J plus K, and AM is just all of that over 2. So I over 2 plus 1 is going to be 3 over 2. So 3 over 2 I plus J plus 1k minus 1, it's just going to be 0 plus 0. So all we're left with for OM is 3 over 2I plus J. Cool. Nice and easy there. Pretty tedious, but overall, I think pretty simplistic. Okay. Now we want to find the angle between OA and M. So, it's this angle here, probably. Actually, it's probably this angle here. The way we know what angle we're looking for is that it's whatever the middle one is. So in this case, it's the angle near A. So O, A, and then M. Makes sense that that angle there is the angle we're looking for. So what we're doing is the dot product between probably OA and AM. So OA dot OM divided by the magnitude of OM dot OA sorry, my handwriting's kind of gone whack here. And then now we just plug that into cosine theta. I'm not going to work it out, just in the interest of time, because I don't want to get through more content. And for BMO, what we do is we're trying to find this angle here. So B, M, and O. So what we're doing here is now the dot product between MB. Oh, actually, we're doing the dot product between probably B to M. That gives us one vector, and M to O. Yeah, we're going to be doing the dot product between BM and MO. And we're dividing that by their magnitudes again. BM, MO. Equate that to cosine theta. Once you work out what this is, you do arc cosine, and then you'll figure out your answer there. Okay, so hopefully that made sense. Again, feel free to ask questions if it doesn't. All right, linear dependence. This refers to when, we can describe one vector with a set of other vectors. For example, OM, in this case, can be described by a set of other vectors, right? Pretty easily. Linear independence is when you can't. It's I guess it's kind of makes sense. For example, with see these set of three here are linearly independent. However, because we can't exactly describe them as a combination of the other, right? However, we do need to multiply and stretch and squish them before they can be linearly dependent. So that is our rule here. So to figure out linear independence, the first thing is we need to write our linear independence formula down, and then write all our vectors in matrix form. And then, so the reason we do it in matrix form is just because it's a bit easier to see. And then multiply everything in, and then make a set of simultaneous equations, and then solve those three pairs of simultaneous equations for M and N. If two things are linearly dependent, there exists a value for M and N. If they're independent, there doesn't exist a value. Sorry. If they're linearly independent, there doesn't exist a value for M and N. So it doesn't work, linear independence. Does work, linearly dependent. P refers to the term in front of C. Usually we can just, set P as equal to 1. Usually we can set let P equal 1, and then it doesn't matter anymore. So, yeah, pretty nifty. Okay, have a go at this. I'll give you guys a couple minutes. Sorry about that. Okay, hopefully that was enough time there. So let's start working through this. Okay, so we want to know that, or we want to find out if there exists MA plus BC. Oh, I'll just keep the same conventions as before. So NB is equal to PC. We want to know if this exists. You could include P. It doesn't really matter. Because we have three sets of equations, right? So we can solve this including P as well. But it doesn't really matter. Just to simplify the situation, we can say P is equal to 1. Because these are arbitrary numbers, right? It ultimately doesn't really matter. And so then we can get our set of equations. I'm just going to multiply this in here. So pretend like there's an M and an N there. So we'll get 4M plus 2N is equal to negative 4. M minus N is equal to 2. 3M plus 3N is equal to 6. All right, so we have three equations, two variables. So we can choose any two equations and fiddle around with that to see if we get our answer. I'm going to choose the last two equations just because I think they look a little bit similar. So I'm going to choose 2 and 3 to do my maths. What I want to do first is I want to divide 3 by 2. So divide equation 3 by 2. And that's going to give me... Oh, actually, sorry, not 2. Divide it by 3. My bad. So yeah, I want to divide that by 3. And that's going to give me... That's going to become n. And that's going to become n. And this is going to become 2. Okay. So we will get m minus n is equal to 2. And m plus n is equal to 2. Okay, weirdly feels like a contradiction, but let's just go with it. So next I'm going to combine both my equations here. So we'll get 2m is equal to 4. And then m is equal to 2. Okay, and I can plug that back in here to resolve. So plugging m into there, I'll get 2 plus n is equal to 2. And this tells me that n is equal to 0. If I plug it into here, same answer, pretty consistent results though. So we found that, m is equal to 2 and n is equal to 0 in two of these equations. And the very last step is to take it and plug it into this equation here and test if the instance is correct. So chucking in m is equal to 2 into this, so 4 times 2 plus 2 times 0 doesn't equal negative 4. Just by looking at it, we can tell, right? Therefore, A, B, C are linearly independent. Oh, I'm just going to write L, I. So that just means linearly independent. That's not like an actual definition or anything. I just made that up on the spot, like Li. Try not to use that on your exams. I just did it because I don't want to write out linearly independent. So hopefully that makes sense. So just a general approach: multiply everything by m and n, then do some simultaneous equations with it on 2 of the equations, and then use the last equation to check if everything actually fits and works. Okay, have a go at this one as well. I'll create a poll for this one as well. Are they... I don't want multiple choice, I want word cloud. Are they independent? Okay. Have a go at this. Chuck your answer up on that word cloud, and we'll see what everyone gets. Okay, let me see what the answers are so far. So not linearly independent, and so we got one that says not linearly independent, and another answer that says yes, they are independent. Alrighty, let me have a go at solving this, and we'll talk about it. All right, so again, I'm just going to write the m and n in front because I'm lazy. And so what we'll have here is m plus 3n is equal to 3. M minus n is equal to negative 5. Minus m plus 4n is equal to 11. All right, so I'm going to use the last 2 equations because I can just add them together and cancel out the m's, right? So I'm going to add these 2 together. So I'll get 3n is equal to 11 minus 1 minus 4. And again, I'm only doing this to try to eliminate silly mistakes. So then I'll get 3n is equal to 6. And so that tells me n is equal to 2. Okay, cool. So then here I can do the same. So then m minus 2 is equal to minus 5. And then m is equal to minus 5 plus 2, which is equal to minus 3. And the last step is to check if it's consistent with what we have here. So minus 3 plus 2 times 3 is equal to 3. Yes, this is true. But I'll work it out entirely anyway. So minus 3 plus 6 is equal to 3. So therefore, no. Since there exists an m and an n, they are linearly dependent. So they are L, D. Linearly dependent. Let's have a look at what everyone else said. Yeah, not linearly independent. Nice. That should be the predominant answer there. So good job to everyone who got not linearly independent or linearly dependent. I'm a bit interested to see why people got that they are independent. Feel free to throw that in the Q&A area, or maybe, chuck it up into the cloud itself as to why they got independent. Maybe I could have made a silly mistake. That's entirely plausible. So I'll double check my working out just because I don't want to have made a silly mistake. So m plus 3n is equal to 3. Again, because we're assuming p is equal to 1. M minus n is equal to negative 5. Negative m plus 4n is equal to 11. Again, add these two, so that should be 3n is equal to 6. N is equal to 2. This one is going to be minus 3. Yeah, that makes sense. So then minus 3 plus 2 times 3. I'm pretty sure, since m and n do exist, I'm pretty sure they should be linearly dependent. Feel free to correct me if I'm wrong. Yeah, because it's entirely possible. Maybe send me an email if I'm wrong or something. If I do get any of these questions wrong, just feel free to send me an email, and I'll have a look at it again. Okay, so that is that. Let's move on to vector projection and vector resolutes. So let's say, we have like two beams, right? Like a wood part and a floor part. And I sort of want to know what the difference is between those two, or how can I break up this wood into two separate sort of vectors, right? So let's say, we have this wood like part and I have the floor, and the wood part is obviously going to cast a shadow, right? It's going to cast a shadow on the floor, right? The sun is above. And we can figure out the shadow and the height of that wood area using vector projections and vector resolutions. So what it actually does is that, just get our laser pointer, is, what vector resolutes asks is, what is that shadow cast by A on the second vector B? So we're trying to find what component of A is parallel to B. Generally, or alternatively, we're trying to break down A into its like parallel and perpendicular components. So ideally, adding U and W will give us A. We're just trying to find those components. The main sort of like question type that comes with this is like shortest perpendicular distance. So yeah, that's what we should be sort of thinking about whenever we see, the key term shortest distance or perpendicular distance. We should always be thinking vector resolutes. Earlier today morning, I was answering a question by email. Someone had sent me, they were asking like, was like, how do I know what technique, or how do I know what like topic to apply, when I get a random question. And I was like, thinking about, well, how did I do that? And one of the things I was using was keywords. So shortest distance, I always linked that to perpendicular distance. Whenever you hear shortest or perpendicular distance, you should always be thinking resolutes or vector projections in Specialist, especially if it's under like, if it's clearly like a vector topic. Yeah, so you should be thinking of. All right, so the vector resolute of A in the direction of B can be represented by the vector U. And all we do is, what we're doing here is we're finding the magnitude of, finding that magnitude of U, or the magnitude of A, and we're multiplying it in the direction of B effectively. So the way we do that is we take the dot product and then divide it by the dot product squared, and then times that by the direction of B. An alternate way to write this out is, this here is the dot product, so A dot B times the unit vector of B. So B, that there is a unit vector of B effectively. Unit vector of B sort of squared. Okay. Yeah, so that is probably better. So that's really what's happening here. Okay, so just as long as we keep this equation here in our minds, we should be good to go with vector projections and vector resolutes. The scalar resolute is just the size of U. Should have two pipes though. Yeah, that's all there is to that one. You can see, we're just multiplying by this extra element, which is the unit vector, which gives us our direction, like I was saying earlier. So all it is the length of U times the direction of B. I'm just going to put the hat under here, so B hat. Okay. Well, how do we come about this equation? Why is it like that? Well, I think the best way to work this out is via trig. Okay, so we have our angle theta here, right, between our two vectors. I want to try work out what U is, right? I already know what B is, so I just need to work out the magnitude of U, and then after working out the magnitude of U, I can multiply it by the unit vector of B, which gives me its direction, right? So the magnitude of U, well, how would I work that out? Using A, because I don't know what W is. I want to use A to work out the magnitude of U. If you guys remember SOHCAHTOA, that's what I can sort of use here. In this case, it's going to be adjacent over hypotenuse. So I'm going to use cosine theta. So cosine theta is equal to the magnitude of U over A, or the magnitude of A. And so I can multiply this to the other side. So then I have the magnitude of U is equal to A cosine theta. Okay, so how can I, given that I don't know what U is, how can I bring B into this? And the way people thought up was, well, I can multiply both sides of this equation by the magnitude of B divided by the magnitude of B. So I can do this. This is going to be equal to sorry, this is taking me a while to write all of this stuff out, but hopefully it's making sense. All of this is over B, or the magnitude of B. Cool. I just wrote this in just for clarity. Obviously, all of this here is just going to be 1. Technically, this is 1 as well, but what we can do is we can collect this term as a whole. So that becomes A dot B, and that's divided by the magnitude of B. And so that's where we get our scalar resolute from. And the very last thing we have left to do is give it a direction. And to give it the direction, we just use the unit vector of B. So hopefully that makes sense, the way I got around to sort of deriving what the scalar resolute is and then deriving what the vector resolute is. The vector resolute was never a formula I remembered. If I needed it, I could always just derive it. So that's like, I guess the benefit of understanding, the content really well, is whenever you need like a bit of content, all you need to do is derive what you need. And to work out what W is, we can just do vector addition. So I just subtract U from A, and I'll end up with W. Alrighty, I'll let you guys have a go at this one here. I'll give you a couple minutes, not too long, maybe a minute or so, to have a go at this. I'd say just plug it into the formula here. If you do want to have a play around with it, feel free to use first principles and derive it from scratch like I've done here. But just for simplicity, let's just chuck it into the equation. Alrighty. Hopefully that was enough time. So all we have to do really here is just chuck it into our formula here. So first thing I'm going to do is do A dot B. So A dot B is going to be 1 times 1, so 1. So it's going to be 1 times 1 here, so 1 for the I component, plus minus 3 times 0, and 0 times, because remember we have a 0j component here, 0j. So it's going to be 0 times minus 4, so it's going to be plus 0. And for our k component, it's going to be minus 3 times positive 1, which is going to be minus 3. So I'll just write this down. So A dot B. Also, instead of computing it all together, it's a little bit useful to work everything out in smaller bits, which is what I'm going to be doing here. So 1 minus 3, and that's going to give me negative 2. All right, next I want the magnitude of B. So the magnitude of B is going to be equal to 1 plus 4 squared is 16, plus 1, and the square root of this. And this is going to give me 2 plus 16, which is 18. So the square root of that. All right, so now my vector resolute is just going to be square root of 18 times the square root of 18. So 2 over square root of 18 squared times I minus 4j plus k. And this is going to be 2 over square root of 18 is obviously just 18. Square root of 18 squared is obviously just 18. So it's going to be 2 over 18, which we can simplify to 1 over 9. And what's left is I minus 4j plus k. So yeah, too easy. And we're done. Vector resolutes are probably 2-3 mark questions. So if you can do that pretty quickly and accurately, that's pretty good. Sometimes, in some cases, you would have to fully expand as well, but you don't have to always do that. All right, let's have a go at doing this, and then we'll go into break time. Probably can't do the full 15 minutes in break time, unfortunately, just because, it's 12 already. I'll give you guys a minute or two to do this, and then we'll have a crack. The easiest way, I think, to start this question is to draw it out. Okay, let's get started. This one here is a bit more tough, I think, just because we have to somehow convert this line into a vector. Okay, let's draw out the situation. So we have the point 1 and 2 root 3. So it's probably somewhere here. And our graph is going to pass through 1 over 1 sorry. It's going to pass over 2 over root 3. I'm just going to quickly rationalize that. So it's going to become root 3 over 3x. Okay, so it's going to be root 3 over 3x. And so it's just going to, probably not going to coincide much with that. So I'm going to assume it goes a bit like this. All right, that's our line. Let's make a unit vector for this here. Well, I mean, we can use unit vectors to define this point. So this point, I'm going to call it P. OP is going to be equal to I plus 2 root 3j. And I need to find this perpendicular distance, right? Because the shortest distance. I'm going to find this distance. Okay. One thing we can do is choose a random point on this curve. So let's say, let's say x equals, I don't know, something cool. Past 1, obviously. Let's just do x is equal to 2. That's going to give me y is equal to 2 over root 3. That's probably not high enough. We'll need something that's greater than 2 root 3, I think, to make it work. Or actually, would it matter? No, I don't think it matters. That graph is just drawn badly. I'm just going to try redraw it. It probably looks a lot more like this. So we're trying to find that distance there. Okay, so this works. So we can create a new vector. I'm going to call it OL, the line, I guess. That's going to be 2i. I could probably, just because I want its distance, just because I want its direction, sorry, I can even use x is equal to 1. It doesn't really matter. So we'll do x is equal to 1. So I plus root 3 over 3j. Let's just use 1. So we'll just cross all of that out. Okay, so let's look at our formula again. So we want to know the dot product first. So we're going to take the dot product between these two. So OL dot OP, that's going to be 1 times 1 for the I component plus 1 over root 3 times 2 times root 3, which is just going to be 2. And that's going to give me 3. So that's our dot product there. And then what we want is the magnitude of B. So the magnitude of B in this case is going to be 1 plus 1 over 3, the square root of that. And that is going to be 3 plus 1, so it's 4 over 3. That there is all under a square root. So here, that's going to be, I'm going to pull out the 2 from this, so it's going to be 2 square root 1 over 3, or alternatively 2 over square root 3. And then all I need to do here is find that denominator, and to find that denominator, I'm just multiplying by twice. So it's going to be 2 over root 3 times 2 over root 3, which is going to be 4 over 3. So right now what we have is 3 divided by 4, which is going to be divided by 3. So that's going to end up as 9 over 4. And obviously we have OL here. And so then the last step is just to combine everything. So I plus, oh, actually, we don't even need to go that far. Okay, doesn't matter too much, I think. So I'm just thinking about this. Yeah, actually, I think we can stop at this point here. Because what this here, we just need to figure out. We just need to figure out what the scalar resolute is. And that's going to be 9 over 4. And now, what's nifty is we can use Pythagoras theorem, right? So we have 9 over 4 here. And now all we really need to do is find the magnitude of this, which is going to be 1 plus 12, because that's going to be 4 times 3. Square root of that is 13. So now what we have here, so square root of 13, we have a triangle like this. We want to find the shortest distance, right? We know this side is 9 over 4. Sorry, that's a dividing line. And we know this side is square root of 13. So what we need to do is just Pythag, really. So this is going to be, so right at the top, 13 minus, that is going to be 81 divided by 16. Square root of that should give us our answer. I've probably made some mistake here in the maths, but the general idea is the same. We want to choose some vector on this line. So the easiest way to do that is plug in 1 and find your y coordinate. Create a set of 2 vectors, and then use that to find the scalar resolute, and then you can use Pythagoras theorem to find out the perpendicular distances. Alternatively, you can find out the vector resolute, and then get your original vector and subtract it from your found vector resolute, and we'll get this. And then you can find the magnitude of that. I just thought it might be easier to use Pythagoras theorem, but now I can't be bothered to multiply that and work it out. I am sorry if I didn't make any mistakes there. Hopefully not. All right. So complex numbers time. So complex numbers, they're generally a number that includes some real numbers and some multiple of the imaginary number. The imaginary number is represented by I, and it is the square root of -1. Right. So square root of -1. That is known as I, or the imaginary unit. Complex numbers are written as these equations, and the equations are x, which shows the real axis, and that's your on the complex plane. The real axis is x, and the complex axis is y. So yeah, it's just an equation. Y is still a real number. However, it's being multiplied by -1, which is why it's scaled on the complex plane. The conjugate in a complex number is just when we flip the sign in front of y, and it's just given by a z bar. These are just some quick complex number properties. So if we multiply two conjugates together, we get the magnitude squared. Again, the magnitude is the same as the vector. The magnitude of z is just going to be x squared plus y squared. It's pretty nifty because complex numbers can be treated like vectors in a sense. And there are some certain question types that you guys will run into across that will require you to use complex numbers the same way as vectors. They don't have a direction, so we just label it with a like a round bit. Here is x, and here is y. The reason it's magnitude is, again, using Pythag theorem because it's all triangles, right? So we can find, its length by using Pythag theorem. Okay, I'll let you guys have a go at this in your own time. Again, if you had any questions with, these questions, feel free to shoot me an email. And I'm happy to make solutions for you guys, or help you guys with any of these. So yeah. All right. One thing I will talk about is division. I'll let you guys have a go at that. Or actually, probably not, just in the interest of time. I'm gonna skip past all of this. This is just solving complex number equations. You guys will come across, like this one here. It's gonna give you a negative. And this one here, you'll notice that the determinant is less than 0, so you will have at least one complex solution here. So yeah, have a go at these. With this one, you can convert it into polar form and then divide. Alternatively, with division, you just multiply it by the conjugate over the conjugate. But I would, whenever doing multiplication or division, it's just always easier to convert to polar form. And I'll talk about polar form if you guys don't remember what that is pretty shortly. Also, that plane there is called the Argand diagram. It's just like, I don't know, weird complex number stuff. It's just how they like to represent things. Whenever we multiply things, it's always an anti-clockwise rotation. And this line here is known as a ray. And so we always draw rays as solid lines. Everything else should be drawn as a dotted line, and the coordinates still work the same. Okay, so this is what polar form is. I'll probably just cover that in the last couple seconds that we have. So polar form is when we convert this Cartesian form into a form that uses the angle and the magnitude. So we're describing this complex number in terms of the angle it makes with the Argand, x-axis, and the length it is at. So r is just the magnitude, and theta can again find this using Pythag, or I'm not Pythag, SOHCAHTOA. So y divided by x, because opposite over adjacent. And yeah, when we divide and multiply anything with these, so with polar form, when we divide things, what we can do is we divide the r's, so r1 divided by r2, and then we subtract the angles. So cis theta 1 minus theta 2. And when we multiply the r's, so r1 times r2, and the angles are added instead. Alrighty, so hopefully that makes sense. There's a lot more, a bunch of notes for you guys to go through. So have a go at that. Have a go through the rest of these slides. So yeah, unfortunately we couldn't cover everything today, but that's pretty expected usually. But yeah, I'll just check if there are any more questions on Slido. Um, all right, neat. If that's all, feel free to shoot me an email. I'm always happy to respond. Go through those notes. Definitely pretty useful. Have a go at doing all those questions, and yeah. Good. Best of luck with year 12, and hopefully see you guys around. Bye bye.